Okay. Okay, so let's continue after this silly interruption. Okay, let's do the following corollary. Okay, I have a ring extension. Okay, then I look at the set A twiddle consisting of the elements of the bigger ring B that are integral over A. Okay, and the statement is this is a subring of B. This is subring of B containing A, of course. Okay, so what we need to prove here that if I have two integral elements and I take their sum, their difference, or their product, I get integral elements. Okay, so how do I prove that? You see, that's not completely obvious. So let's assume I have two integral elements. So then I take the sum. So how would you find such an equation for x plus y? Okay, or for the product? It's another trivial computational task. So there is some idea here. And the idea is to go via this characterization, which I have in this box here. That's the idea. So what I do is, so I look at the subring generated by x and y over A. And by the proposition, this is finally generated as an A module. Finally generated A module. This is the proposition. Okay, 5.2, the one I just proved. Okay, so now, okay, now this will be my C. Okay, and then I apply the following principle. Right, so now I conclude with our criterion, that was the proposition 5.1. I conclude that x plus minus y and x times y, they are integral over A, since I just use the following. So let's say I have this. Okay, this is in C, or put a minus, or this. Okay, so you see, I have an intermediate ring. It's finally generated as an A module, and it contains the element of interest. Therefore, these elements are integral. Okay. Okay, so this A twiddle is a ring, and it has a name. It's called the integral closure of A and B. One calls A twiddle the integral closure of A and B. Okay, good. So on those rings, okay, so if you have, right, if you have this, A twiddle equals A, so this means the only integral elements of B are the elements of A themselves. In this case, we call A, we say that A is integrally closed in B. Then say that A is integrally closed in B. So this is a relative notion, okay? So it's not an absolute notion of the ring A, but it refers to the extension, okay? Good. And then we say, okay, if A twiddle equals B, then we say that B is integral over A. Say that B is integral over A. Okay, so it means for all x in B, X is integral over A. Okay, so this corresponds to the notion of algebraic extension. Okay, so we had, there's an example. We showed that the integers are integrally closed in the rationals. Or more generally, if you remember, I mean, this relied on the property that the integers are factorial. Whenever you have a factorial integral domain, it's integrally closed in its field of fractions. Okay. Questions on that? Okay. So another property. Now the transitivity of integral dependence. It's almost done, but this is transitivity. So we know it already for finite, models that are finitely generated. Now we get this. So let's say A is a subring of B is a subring of C. So these are ring extension. Okay, then, so if I have B integral over A and C integral over B, then it follows C is integral over A. Okay. So what do we have to prove here? Looks, okay. So there is, let me do it. There is only a little catch here compared to what we have done before. Okay, we don't assume anything about finitely generated. So let me first, okay, let's take an element X in C. Okay, so since X is integral over B, so I have an equation, an integral equation, write it with coefficients in B. Okay. Okay. So now I note then X is integral over the subring generated by the coefficient over A. Over, let's call this ring B prime. This is A and generated. Now here I put the coefficient. Okay. Okay. This is a subring of B and it is finally generated over A. Okay, so now proposition 5.1 tells me that, okay, B prime, when I adjoin X, is a finally generated B module. Okay. And by the corollary 5.2, okay, what is this thing? Also B. Maybe I should write it this way. My B prime, which is this, is a finally generated A module. Okay, so now I use the transitivity of finite generation of modules. That was the proposition 216. And what I get is this B prime, I adjoin X, is finally generated A module. Okay, and then I'm done. Okay, use proposition, our criterion. So in this proof, right. So, but you notice, I mean, what we use all the time is this proposition 5.1, this Nakayama criterion. This is really the key. Okay, what else? Okay, something maybe not too interesting, but for the sake of completeness, let me write it. So if I, okay, it's a kind of a saturation property. So I have a ring extension. Okay, and then A tilde, A twiddle is the integral closure of A in B. Okay, in B, as I said, it's a relative notion. Then A twiddle is integrally closed. Okay. What do I want to say? This is integrally closed. What did I want to do? Closed in B. Okay, and the proof, I mean, there's not much to, what do we have to prove? It's in a way trivial. Okay, I think I don't put the proof. I mean, it's trivial. So you have this ring extension. Then you go to the subring of all elements that are integral over A. Then what you get is integrally closed. You cannot enlarge it further, okay, with the integral elements. Okay, so one last thing, this integrality of ring extensions is really nice. Okay, it is preserved when we go to quotients or when we do localization. So this is very useful. It's very easy to show, but very, very useful. This is proposition 5, 6. Okay, so I have an integral ring extension. Okay, so what I can do, okay, I form quotients. Let's see, B is an ideal of the ring. Then I pull it back. This I call A. Okay, is an ideal of A. Then I get a homomorphism of the factor rings, which is injective. Okay, this is injective. And this is then an integral ring extension. Okay, so as it should be, second statement, this refers to localization. I take a multiplicatively closed set, so S in A multiplicatively closed. Okay. Then I do the localization of A, but I can use the same set for localizing the ring B. Okay, then this becomes a subset of the other, and this is an integral ring extension. So it's clear that these are useful properties. Okay, and let's do the proof. Really simple. Actually, there's nothing to do. So for x in B, I have an integral equation. I can write it. Okay. The coefficients in A. Now I just apply my homomorphism. Okay, I go to the factor ring. This is the canonical homomorphism, and that's it. I still have an equation. It's still monic. The coefficients are now in the residue class ring, as in the factor ring. And it's an equation for x mod B, right? So there is nothing, that's all. In a way, it's trivial. Okay, then for the second property, I take a general element of the localization s to the minus 1b. So x is in B and s is in capital S. Right, and then, okay, x is integral. So I use this equation that I have for x, right? But I want to have an equation for x divided by s. So what I do, I just take this equation and divide by s to the n. Okay, or I can say multiply. Let's put here a star. with s to the minus n. Oops. Okay, and then I get this. I write it in this fraction notation. Then I have a1 divided by s, x to s, n minus 1, and so on. Okay, and then we see, now I have an equation where the coefficients are in this local, this subring, the localization of A, and it's for x over s. So I get this is integral over this ring. Okay, and I'm done. Okay, questions on that? No questions? Okay, so what we are going to do now, we investigate the behavior of prime ideals with respect to integral ring extensions. So the keyword is the going up theorem. There is also a going down theorem, but I decided to skip it for lack of time. So let's go to the next section, which is the going up theorem. Going up theorem. Okay, I think it's due to Seidenberg. Maybe move it down here. Good. So it goes, okay. I will give the statement a bit later on. Let's go in steps. So let's put the pieces together. So I think it's quite nice, this chain of arguments. So I like it. Position 5, 7. It's very classical, but I'm telling you. So let's assume I have a integral extension. And these are integral domains. So these are integral domains. Well, no zero divides from P is integral over A. Okay, and the statement is A is a field if and only if B is a field. Okay, this is okay. Okay, good. So how do we prove that? Two directions. So I assume A is a field. I take a non-zero element y of B. I have to prove y has a multiplicative inverse. Okay, and how do I get this inverse? Well, I use that y is integral over A. So I have such an equation. Blah, blah, blah. Coefficients in A. Now I can use, what can I do? Okay, let's say with minimal n, that's useful. Minimal degree n, then I'm sure that the an is not 0. Otherwise, I would say, I could divide by an. Well, I would use that A is an integral domain. Okay, I get an. Okay, I can remove, otherwise I could remove the an. So the an is not 0. Okay, here I use the integral domain. Otherwise, I couldn't make this conclusion. Good. So now, but now I can write. Now I use that A is a field. So this an, which is non-zero, has an inverse in A. And then I use this to get an inverse. Okay, I just write. You will immediately check that what I'm doing is correct. Because I can now write an inverse of y. So, oops. So what I do, So I move an to the other side of the equation. And then on the left-hand side, I get y times something. So the y times something is minus an. Okay, then I multiply with minus the inverse of an, and I get this. So what I see, so this is an inverse. So, okay, up to this. So I see, okay, therefore y has inverse.
Isn't it one y too many?
Sorry?
You have one y on the left of the bracket and one y on the right.
This is in fact, good, you're right. Thank you. There was one too much. Let me also remove it here in my notes. Thanks. I see you can follow. Okay, this is one direction and the other. So I show this is a field and the other. So now I take an element x of A, which is non-zero. I know x has an inverse in B, but I want to have that the inverse is in A. Okay, so since B is field, I have the inverse, but a priori it's in B. I have to show it's in A. Okay, so what do we do? The x to the minus 1 is in B, so it's integral. So I have an equation for x to the minus 1. So I have some equation of this kind. Okay, maybe I put here a prime, so to distinguish from what I had above. I have such an equation. The AI prime are in A. Okay, so now I multiply with x to the m minus 1. Okay, then what is nice, then what I get here, like this first contribution becomes x to the minus 1. So the other stuff, okay, after multiplying, I put on the other side. So if I didn't miscalculate, it's this. Okay, so what I see, this is the inverse of x, is actually an element in A. Okay, the coefficients are in A and x is in A. Okay, so I see A is a field. So this looks all terribly abstract. Now it occurs to me, anecdote or a story. This idea is actually useful in computational linear algebra. So right, let's say you have a matrix. Okay, matrix is maybe, I'm not in a commutative ring, but it doesn't matter. And you want to compute the inverse, right, of a matrix. And assume for some reason you have, maybe you have the characteristic polynomial, the minimal polynomial, or just such a polynomial relation, such a thing, okay? Then you see, now if you look at this trick that we have done, yeah, you can write the inverse as a linear combination of powers of y. Okay, so this idea that we used here in this purely structural proof is actually computationally useful, is very useful, okay? Okay, right, I just wanted to mention that. So in a way, these are very old ideas that people at some moment realized I can use in numerics or computer algebra. Okay, it was just a comment.
Can you maybe repeat why we could assume that an isn't 0 in the first part of the proof?
Where are you exactly?
The first part of the proof, so the first direction.
The first direction. Okay, why an is not 0?
Yes.
Right. So if it were 0, let me write it maybe with yellow over there, then I could, right. Okay, then it would look like that. But then I can pull out the y, because what I have,
Okay. Mhm.
right? And now, because y is non-zero, okay, it follows this must be zero, because y is non-zero. And I have an integral domain. Okay, good. Another question? Okay. Okay, but it just occurred to me, I did an algorithm called Wiedemann's algorithm. This is for solving, say, you want to solve a system of linear equations over a field with two elements very efficiently. Huge matrix, but very few entries. This is used in cryptography. And the idea exactly uses this. Because there are more things, but it's this idea. Okay, just to let me say that in so that the lecture will not so terribly dry. Okay, so let's apply this principle from before, corollary 5.8. Right. So, okay, I have a ring extension, an integral. Okay, B is integral over A. Okay, and then I take a prime ideal. So we had this notation spec. So I write Q is in spec B. It just means Q is a prime ideal of B. Okay. Then let's say P is the contraction. P is Q intersected with A. So this is a prime ideal of A. Okay. Now I'm wondering, when is Q a maximal ideal? Okay, when is Q a maximal ideal of B? And the statement is this happens if and only if P is a maximal ideal of A. Okay. Um, okay. The proof, okay, is very short and elegant. So I go to factor rings. I look at A mod P. I can view this as a subring of B mod Q. So basically, I look at I have the canonical map from B to B mod Q, restrict to A. It will be injective and the kernel is P. So I have this. And this is an integral extension. This is integral ring extension. So for this, I use, I just use this, where is it? I mean, this proposition 5.6, actually part 1, this trivial one. This is proposition 5.6. Okay, right. But then I know, what do I know? Q is a maximal ideal if and only if this is a field. Okay. But I know by the proposition 5.7, is it? This is a field if and only if this is a field. Okay, so this means exactly P is a maximal ideal if and only if Q is a maximal ideal. Okay. Write it a bit nicer. Okay, good, good. Right. Question? So now let's go to the next result. And I think that's really nice. And this is essentially, this is the essence of this going up theorem. So in a way, let me mark it with somehow important. So, okay. Tell me how I can get prime ideals. So I have an integral ring extension A to B. Okay. Then I assume I have two prime ideals, Q and Q prime of B. And the one is included in the other, such that Q is contained in Q prime. Okay. Okay. So, okay. And let's assume, so if I contract, so I intersect with A, then I get equality. This is the assumption. And the claim is, if this is the case, then Q must be equal Q prime. Okay, so you have, in the big ring, you have two prime ideals, one contained in the other. Then you contract, you look down in the ring A, and you happen to get equality. Then you have equality upstairs. This, yeah. Okay. So in a way, but it says that like the prime ideals, I mean, up in the bigger ring are determined by the prime ideals down there in the smaller ring, provided you have this inclusion relation. Okay. Good. So how do we prove that? So this is right, a nice application of this principle. Yeah. I mean, how can we are going to reduce this statement to what we have shown just before. And the way we can do it is by using the principle, the method of localization. Okay, so let's say P is this common contraction. I just give it a name. Okay, then now I look at the localization. So, okay, maybe. Okay, do right. Perfectly clear. I look at the multiplicative set A minus P. And I look at the localization. Okay. Maybe I go, sorry, slowly. I look at this localization. Okay. So we have an inclusion. So why is it an inclusion, by the way? Does anybody, are we sure? A is in B. Now I do this localization. Why is it? Sounds like a silly question.
Probably if you ask that way, then it's the universal property.
Oh, not quite.
Okay.
So, I mean, what I have like the inclusion, okay? It's injective. What we learned, now what we apply is this functor, okay? We go, okay? So this is, if you remember, we have a functor, okay? We can also, that this localization not only assigns new objects to here rings, but also to ring homomorphisms. And we know it's an exact functor. So in particular, if this guy here is injective, this must be injective as well. Okay, injective is preserved. Surjective is also preserved. So of course, this is just to, this is what I applied. Right, and so this thing, I mean, this used to, let's call it, this is AP. Okay, this is our standard notation. I localize a ring with respect to a prime ideal, and what I get is a local ring. Okay, So AP is a local ring, and the maximal ideal is obtained by extending P. Now it's quite, let's also give it a name. Let's call this BP. This is just a naming, BP. Okay. So good. So this is a local ring. Okay. With maximal ideal. Let's call it M with maximal ideal M. Okay. Good. Now it's good to, let's put a diagram. So diagram and inclusion. Here I have my localization map. Here also the localization map. And I just noted this map is injective. So, and what we have here, so, okay, we have this primary P. Here, I have the maximal ideal M. So I know if I, okay, right. So if I extend P, I get M, or if I contract M, I get back P. So they are closely related. And here in B, I have these two prime ideals, one included in the other. I want to show they are equal. So what do I do? So I look now, instead of looking at B, I look at this localization. Okay, I look what happens with these prime ideals in this ring. So let me write it in text. Let N be the extension of Q in B. Okay, I have some ideal here. Right. Actually, we know, I mean, I discussed what happens if I have a localization. Okay. I discussed what happened with prime ideals. Prime ideals, either they survive after extension, they will be prime ideals, or they disappear. Disappear meaning they get the whole ring. Okay. So in this situation, the prime survives. So note, this is different from B, since the Q, okay, doesn't contain elements of S. This is empty. Okay. Otherwise, I mean, you see, if this would be wrong, I would have an element of A, which is in Q, but then it's in P. But this cannot be because it's in S, outside of P. So I have, okay, this condition makes sure, so N is a prime ideal. So N is a prime ideal. Okay, now I play the same game with N prime. Let N prime be the extension of Q prime in B. Also, okay, so I get, therefore also this is not B. And now I write it in my diagram here. So I have in this ring here, these two prime ideals, one containing the other. Okay, so maybe I can write it here in the text.
One question, why don't you write B sub P?
B sub P, or?
Yeah, shouldn't N live in B sub P?
Yes. Okay, you are right. Thank you. That was a typo. Thanks. Okay. Good. Now what happens? Now let's go. I mean, what is the trick in the diagram? Diagrams are good. They tell us what to do. We went from here to here. Now we go from here to here. So it means contracting. So I contract. So I go to the ring AP. But clearly I have this inclusion here. This is contained in the M. right? Because I mean, you see, okay, the P is contained in all these guys, okay? The P is just everywhere and also in M. Okay, so the P is contained here, so therefore the ideal generated by P in AP, namely M, is contained. So I have this. Okay, and the point, these are prime ideals. Okay, these are prime ideals of AP. Okay, again, I mean, I use something. I mean, and I'm very detailed now. I have N. Okay, it's a prime ideal. I contract, I have a prime ideal. Okay. Actually, I don't need it's a prime ideal. I only need to know that these things are not everything. They are not AP. Because now I can use that M is a maximal ideal. Okay, AP is local. So this tells me that I have equality. Okay, good. So what? But now, right, now, okay. But this proof is really nice. Now we look at, okay. Now let's have a look at this extension. This is an integral extension, okay? So maybe I can write. So integral extension. Okay, I have here an N and I contract it. Oops. Okay, what I want to say now that N, okay, now, right. Okay, I conclude now with the corollary 5.8 that N is maximal. You see, this is exactly the situation. I have this ring extension. I have a prime ideal. Here is the contraction. Because this is an integral extension, I know N is maximal if and only if this guy is maximal. But this is maximal. This is the M, okay? This is maximal. Okay, so I get N is maximal. Okay, yeah, good. Of course, well, right. Now I'm, okay, also by the same principle, M prime will be maximal. I just observe this inclusion. N is maximal, but N is in N prime. So therefore, what I get, N equals N prime. Okay, and then, right. And then if I contract to the Q's, I get Q equals Q prime. And I'm done. Okay. So I use here to remember, okay, what we did. We started with the Q. N was the extension. Okay. If I contract back, I get Q. So these are these general principles, extension, contraction, that we looked very closely in the context of localization. Okay, so any questions for that proof? So I think this proof is very instructive. One can really see how things come together and how localization is a useful concept, okay, within a proof. Right, okay. Okay, so now a theorem. So in this theorem, essentially, I would say this is the essence of the going up theorem. I mean, this is really the important thing, even though it doesn't usually, it's not called going up. Okay, but essentially it's that. So let's assume I have a ring homomorphism F from A to B. Okay. Okay, I didn't say what is an integral ring homomorphism. Maybe I define it right now. An integral ring homomorphism. Integral just meaning that, right, means the extension. Okay, this is convenient, right? Because now I just assume subring fa of b going to be this is integral. Okay, this is an integral ring morphism. Okay, then I go to the comorphism of the spectra. I'm aware I hardly discussed this, but I just gave the definition. So the definition is just take a prime ideal in B, contract, you get a prime ideal of A. So this map is called F star. So usually if I had more time, I would have introduced the Zariski topology on these spectra, on these specs, and then I could show the F star is continuous, etc. But now I don't do this, but I just have the map. Okay, and the statement is this map is surjective. So this means if you don't like spec and you don't like F star, it just means the following. For all prime ideals, okay, of A, there is a prime ideal Q of B such that P is the inverse image of Q. Okay. This is the statement. So if, for instance, okay, in the most applications, A is actually a subring. So F is the inclusion. Okay. So then what you have here, you have down here, you have your P, your prime ideal, and up there, you're looking for a prime ideal up there, a Q. And the relation is, well, okay, usually we say Q is lying above P, okay, and the point is you want to have, maybe I should write it here in orange, you want to have this, okay, lying above. To make it more intuitive. Okay, it says over every prime ideal of A, there lies at least one prime ideal of B. Usually there are several. Okay, this is a situation, by the way, which is, it occurs very prominently in algebraic number theory. Okay, when the A and B are number rings. Okay, so let's prove that. It's another. Okay, essentially the essential work is done, but it's also another example of to see in a proof where we can use these concepts of localization. So what do we do? P is in the spectrum of A. Parenthesis. Then I look at the following commutative diagram. It's always good to look at diagrams. A to B, this is F. Then I'm going to localize as before. So I use the same notation A, B, B, P. It's the same thing. And the corresponding map I denote by FP. It's just a localized map. And here I have also canonical maps, alpha and beta. So I have this commutative diagram. Okay. So here we have P. Okay, the prime ideal. Let's see. And what we want to have over there, we are looking for a Q. Okay, where is it? How can we find it? So what we would do naturally, like, okay, in the diagram, let's go down first. So I want to define an M. Well, what is M? M will be the maximal ideal, right? Okay, M will just be the maximal ideal of my local ring AP. We had it in the other proof. Okay, and so let me, okay, for the logic, let me write it this way. Let me start with the N. So there is also an N here. So let N be a maximal ideal of BP. We can go. Every ring which is non-zero has a maximal ID. So you need to check BP is non-zero. You check it yourself. So there exists a maximal ideal. And then by the corollary 5.8, we see that if I contract it with FP, I get a maximal ideal, okay? Of AP. So the corollary 5.8, let me maybe go back to check. Right. Corollary 5.8. So what I used here, that this is an integral extension. Okay, as we did before. Right, but I know already AP is a local ring, so M is the maximal ideal of AP. Okay. Maybe I can write is the maximal ideal. It's unique. It's the one. Okay, so I have this picture. Okay, so I note maybe also if I pull it back, the M, I get P, of course. So how would you define the Q now? What I ask you, it's not a difficult question. Just want to check whether you are awake. How would you define Q?
Contraction of N.
Contraction of N. Genau. So define Q is beta to the minus 1 N. So we know it's a prime ideal of B. Good. So we only now we need to verify that it's lying over P. So let me write it down formally. Okay, F to the minus 1Q. Okay, really formally. F is the composition of, no, okay. Right. Okay, sorry. So I can write it. Yeah, I can write it this way. Okay, I did not write one step, but and then I use that the diagram is commutative. And then I resolve this. That's the inverse image of the N, which is the M, and this is the P. So I'm done. So basically, I just go back the diagram. Okay. So the point is, I mean, pictorially, you go from here to here, contract. Then you contract here. You want to show it's P. Well, you just say, I can also contract this way. I go this and this. If I contract N, I go in M. If I contract M, I'm in P. And that's it. That's okay. This is just, I wrote it formally, but that's the simple explanation. Okay. So, okay, this proof is also quite interesting, I think. Questions?
I mean, yeah, I'm not really sure, but my first intuition was to maybe make it simpler by just defining Q as the extension of P with respect to F. But I guess
Yeah.
that only works if P is already a contraction.
Yeah, but
ideal, which we don't know a priori.
Okay, so why? Right. So this certainly, if you want to prove this, this is the first thing you try. Okay. Okay. So where is the problem with this idea?
I think the problem is that we need that P is a contraction ideal.
Right. I think if you try this, you will not, okay, get, it's not clear that you, if you contract back, that you get P. So kind of you have to restrict your search space. If you extend in all of B, it will be somewhere and you don't have enough control. So the idea is we take the extension in this BP. Right, this is the idea. Instead of going to all of B, we only go to BP. And then we have enough control. That's the idea. Basically, that's the idea. Okay. I have the map from A to BP. Okay, so this is just a diagonal map. Doesn't matter in which. You take P, extend, and then contract to B. That's it. All right. Okay. Okay, the best way to understand proof is always to see how would I have proved it. Okay, and then you, most of the times, if the literature you're studying is well done, then you realize there is some problem. And that's why people do it this way. Okay, then you learn. Okay, but sometimes it may happen that you find an easier proof. Sometimes may also happen. Okay, so now the going up theorem. Okay, the best is, of course, you try to do the proof, and then you have trouble doing something, then you can even come up with an example where you see there is this problem. Okay, where you see why I have to do it this way. Of course, this is the best way if you want to understand. Okay, theorem 511, this is the famous going up theorem. Going up theorem. Okay, so this is like the previous result, but with a little bit more information related, right? It's also about P's, and you want to have Q's above, but you want to have them with a satisfying an inclusion relation. So let me state the theorem in generality. It's a bit complicated to state, but I will make a picture, then I think it will be clear. I have from A to B an integral ring extension. Integral ring extension. Okay. Then I take a chain of prime ideals in A. So like P1, P2, up to N. It has length N. Chain in A. Okay, and then I have a shorter chain of prime ideals in B, which is compatible. So this only goes up to M. Okay. M is smaller than N. Chain prime ideals in B. Okay, M less than N. Okay. And such that, I mean, the compatibility is when I contract these QIs, I get the PIs. So this is for all I where this makes sense. And the point is, okay, then I can extend the Q chain to a chain in A, such as the compatibility holds. So then the chain, okay, this is unreadable. So this is the chain up to M, can be extended to a chain. I'm afraid this cannot be a chain. Okay, of length M, such that, okay, for all I, this holds. Maybe let's put it in orange. Okay, so maybe picture. Picture is always good if I have enough. Okay, I have, then maybe here. A, B. So here is this Q chain. Here is the P chain. Okay, but this one goes further up to N. Okay, and what I want, okay, okay, now I put this in red. So I want to have these guys. Okay, and they are all, I mean, maybe I put the little dots here saying that means the above are extensions of, okay. When I contract, I get the lower stuff. Okay. This is the going up theorem. Good. Okay. So proof. Okay, proof. So now if you look at this, then you immediately see that we can reduce to the case. Okay, we can reduce the case m equals, okay, m equals 2 and sorry, m equals 1, n equals 2. That's what I want to say. So this is the situation. Maybe I also put it in orange. So I have in A, I have just 2 prime ideals. And here is my Q1. And what I want to have is the P1, the PQ2. This I want to have. Because if I can do that, I mean, so to say, if I can extend in one step, I just do induction. I apply this principle several times and get it. Okay? If I can go up in one step, you just go up several times. Right? Good. Okay. So now this is the situation. So now if you look at this, I mean, showing if I have a P2 here, showing existence for Q2 lying above. This is what we did in the previous theorem. Okay. So the only additional difficulty is I have to make sure that the guy that I construct here will contain the Q1. So how do I do that? Well, how can I make sure that the ideals I construct contain Q1? Well, I work in a factor ring, okay, mod Q1, then I have it automatically. So, okay, so let's do this. So let's define the ring A bar, which is A mod T1, and B bar, which is B mod Q1. Okay, then I have the extension A bar in B bar, and that's an integral ring extension. Okay. So now I work with these things. Okay. So this is always for the, I mean, for those who come later, I use proposition 5, 6. Okay. So now that which was almost trivial, but now by the theorem, I approved just 510 just before the non-trivial one. I know I can find a prime Q2 bar in the spectrum of B bar lying above, oops, the, okay, the P2 bar. So if I intersect with A bar, I get this. Okay. So now I just have to, from this Q2 bar, how do I get the red Q2? Well, oh, okay, where, maybe I should say where, but that's pretty obvious. Where do I want to say P2 bar is the image. Okay. This is in A, sorry. is image of P2 for the sake of completeness. Okay. So now what do I do? Okay. Now I define, I think that's obvious now. I get the Q2, the prime ideal in B, as I can say construction or inverse image. Let's say contraction of Q2 bar with respect to the map B to B bar. Okay, so I get a prime ideal in B, and clearly it must contain Q1. Okay. So, and immediately to check, when I contract the Q2 with A, I need get P2. That's the proof. So you see here now, if you look now at the proof of the going up theory in total, then you can see the methods, like the tools of commutative algebra we applied here. We used the concept of factor rings. Okay, here we use factor rings. Okay, to make sure that we look on the right ideals containing something. And up there, we use localization. Where is it? Here. Here. To make sure we are within something. So these are these two methods that we use both combined, I would say, in a clever way. I can say that it's not my proof, okay? So, okay. Question? No question. Okay, so right. So as I said, there is also this going down theorem, but I'm not going into it. So, I mean, the going down theorem is, why is it the going down theorem is like, we are like in this situation here. Okay. But then, okay, we have this chain of P's, but then the chain of Q's that is given is will be the red one, and we are looking for this one. Okay, so when we go up, the condition will be what I find upstairs should be contained in a given prime ideal instead of containing this one. So kind of you go this direction. That's why I call going down. Before we went going up. Okay, but it turns out that this theorem only holds under additional conditions, namely you need to assume that you're dealing here with integrally closed rings. So it's the theorem is more subtle and is harder to prove. Okay, so I skip it. Okay, that's it. So okay, I just checked the statement. So for the going down, you need to know that the smaller ring A is integrally closed. Then it works. Okay, but also the proof requires some field theorem, which maybe you may not know, and so maybe trace of a field extension. So I skip it. Okay, so next section. You know, I'm going now quickly. So this is something I cannot skip. It's so important. This is Noether normalization. Let's do it all in capitals. And in this context, let's also do the Hilbert-Nullstellensatz. Hilbert's Nullstellensatz. Nullstellensatz. So I think it was in the exercises already, but I think there was no proof, I guess. It's just the concept was illustrated and so on, but now let's prove it. So there's I'd say quite an elegant proof in this context of integral ring extensions. Okay, so first Noether normalization. So, okay, before stating it, let's give a definition. You may know it already. It's the notion of algebraic independence. Okay, so let's say A is a K algebra. K is a field. Okay, it's clear if okay, K is a field. Then I have elements x1 up to x are in A. And then we say that they are algebraically independent. That these elements are algebraically. Or did we have it already in the context of Gröbner basis and so?
Yes.
We had it, okay. We had it.
But
Yeah,
I think
okay.
it doesn't hurt.
But it doesn't harm to recall it. We say that these are algebraic independent over K. If there are no polynomial relations. So for all F, now this is a polynomial in variables T1 up to TR. This is a polynomial ring, okay? Okay, if I substitute the variables by elements, okay, let's say I have such a relation. So it means polynomial relation, okay, or a linear relation between monomials in the xi. So this is only possible when f is a zero polynomial. So it says there is the only polynomial relation is the trivial one. Okay. So you have this, for instance, if you are in a polynomial ring and the x's are variables, then you have exactly that. That's what characterizes polynomial rings. Okay, this is this notion. So can I go a little bit further because we started 5 minutes late and I had my problem finding my pencil. It's hopefully okay. So what is the Noether normalization lemma? I can state it right now. Theorem. Normalization. I mean, lemma sometimes. Very often, if a theorem is named after a person, it's not appropriate. So this was known to Hilbert already. So I don't know why is it called Noether normalization. So maybe Hilbert just used this. I don't know. Okay, so let K be a field. And A is a finitely generated K algebra, and A, B, finitely K algebra. Okay, good. So it's about the structure of finitely generated K algebras. Okay, so the statement is you can find algebraically independent elements in A. Okay, with the property that, right, if you adjoin these independent elements, let's call them x1 up to, oh, a1 up to a, how do I call it? X1 up to x something. Okay, from this intermediate ring to A, it's just an integral extension. So, okay, then there exists x1 up to xr in A. Okay, that are algebraically independent. Over K. Okay, such that, so in a way I have to put some maximality condition. I mean, maybe otherwise you take no element or just one. You want to take as many as you can. And one way to say it is this way. If I now look at the subalgebra of A generated over the field by these elements, x1 up to xr, then this extension, this is an integral ring extension. Okay, so I think this, okay, this is super important, this theorem, and I can say a little more. Namely, if k is infinite, okay, if I have an infinite field, in most applications it's the case anyway, and let's say, okay, let's give name to generators. Let's say A1 up to AN generate A as an algebra. Then now this gives me information where to look for these x's. Okay, let's say the task is you have to find such x's. And the point is, okay, you can find them as linear combinations of the generators A1 up to AN. Okay. Then we may choose the xi here. So they are in the k-span of these elements. Okay, sorry, A1. Okay. Actually, we did even more. I mean, I want to say almost all linear combinations of A1 up to AN are good. So I put in parentheses, Zariski, okay, whatever this means. For those who know, Zariski, almost all K linear combinations of the generators are suitable. So it means, I mean, say if you are happy with the randomized procedure, it's really not fine. It's not hard to find such x's. Okay, take general linear combinations. Okay, that's also important in practice in computer algebra. So maybe I should not start with the proof. The proof is, by the way, will be very short and yeah. But let me tell you a little bit about this. If you look at it from the algebraic point of view, I hope it makes a lot of sense. Okay, you factor like any finitely generated K algebra, you kind of factor it. First, you extend to a polynomial ring. Okay, this is the purely transcendental extension. Okay, it's like, yeah. And then from there, you go to A, that's an integral extension. So maybe you have encountered, probably not, but I don't know, maybe you have encountered this situation in field theory. Okay, you have a field extension, which is maybe not an algebraic extension. But then you can always do first a purely transcendental extension, which is basically structurally it's a rational function field, quotient field of polynomial ring. And then you have an algebraic extension. Okay. And here, this is the refined statement for rings. Okay, so it's very natural, I think, from the algebraic point of view. In geometry, it's also super important. But now I cannot explain this without, but in algebraic geometry, what does it say? Let's say you have a algebraic variety, affine approach projective, it doesn't matter. Then let's say of dimension R, whatever this means. And then you take a linear subspace of dimension R and project. Okay. And if this subspace and the projection are chosen sufficiently general, this will be a very nice map. Okay, this is called a finite map. So in a way, whatever this means. So this is also the neutral normalization lemma. So it's really one of the main tools for also studying algebraic varieties by connecting them, telling them what happens. First, you know what is a linear variety. You connect the general case using that. So this is okay, really important. But okay, we will focus here on the algebraic statement and the algebraic proof, and that's what it is in the end, mathematically. Okay, questions? No questions. Good. Then let's next time do the Noether normalization lemma on the Hilbert-Neufstellensatz, and I think I should finish next time so that next week, oh my God, we can start with a different topic. Okay. So chain conditions and Noetherianity and so on will be then the next topic. Okay. Then